Welcome to Free Learning Academy. Let's simplify CPU scheduling queues. Imagine a busy railway station during peak hours. Trains are arriving, some are waiting, some are being repaired, and passengers are constantly moving around. Now, think of your computer in a similar way. There are multiple programs or processes all trying to get the CPU's attention, some waiting, some running, some paused for input or output. But without proper organization, this would turn into complete chaos. That's exactly where scheduling queues come into play. Inside the operating system, processes don't just randomly compete for the CPU. They are carefully organized into different queues based on their current state and what they are waiting for. These queues help the OS keep everything structured and efficient. The three main ones you need to understand are the job queue, the ready queue, and the device queue. Let's start with the job queue. Think of this as the entry point of all processes in the system. Whenever a program is submitted to the system to be executed, it first joins the job queue or job pool. The job queue represents the total collection of programs submitted to the system, acting as a pool from which the long term scheduler selects tasks to be loaded into memory as active processes. For example, when you start your computer, multiple programs load in the background. Think of the job queue as a waiting area on the hard drive for all programs that have been submitted but haven't been granted memory space yet. The operating system looks at this queue and decides which processes should move forward and get a chance to execute. Now, here's something important. Not all processes from the job queue can immediately enter the CPU for execution. Why? Because memory is limited. The OS cannot load every process into memory at once. This is where earlier concepts like process states and schedulers come into play. The long term scheduler selects processes from the job queue and loads them into memory. Once that happens, those processes move to the next stage, which is the ready queue. Now let's talk about the ready queue. This is where things start getting interesting. The ready queue contains all the processes that are in memory and are ready to run, but are waiting for CPU time. You can think of this as a waiting line right outside the CPU. Imagine you're at a ticket counter. Everyone in line is ready with money and knows what they want. They're just waiting for their turn. That's exactly what the ready queue is. All processes here are fully prepared to execute. They don't need anything else. They just need the CPU. Let's take a simple example. Suppose you have opened a browser, a music player, and a text editor. All three processes are loaded into memory and are ready to run. But the CPU can only handle one at a time. So the OS places them in the ready queue and uses the short term scheduler to decide which one gets the CPU next. This decision depends on the scheduling algorithm, which we will explore in upcoming topics like first come, first serve, shortest job first, and round robin. For now, just understand that the ready queue is dynamic. Processes keep entering and leaving it. When a process gets the CPU, it moves out of the ready queue. If it gets interrupted or its time slice ends, it goes back into the ready queue again. Now comes the third type, the device queue. This one is slightly different. Not all processes need the CPU all the time. Sometimes a process needs to perform input or output operations. For example, reading data from a disk, waiting for user input, or printing a document. When a process needs to perform such an operation, it cannot continue using the CPU. Instead, it moves to a device queue. Each IO device usually has its own queue. Let's make this clear with an example. Suppose you're editing a document and you click save. Your text editor process now needs to write data to the disk. Instead of holding the CPU and waiting for the disk operation to complete, the process moves to the disk's device queue. While it waits there, the CPU is free to execute other processes. Once the disk operation is complete, the process is moved back to the ready queue. From there, it waits again for its turn to get CPU time. Think of it like this. Imagine you're cooking and you put something in the oven. While it's baking, you don't just stand there doing nothing. You move on to another task. Similarly, the OS ensures that when a process is waiting for IO, the CPU is not wasted. Now, if we connect all three queues together, you'll see a flow. A process starts in the job queue. If selected and loaded into memory, it moves to the ready queue. From there, it gets CPU time and starts executing. If it needs I/O, it moves to a device queue. After the I/O is done, it comes back to the ready queue. This cycle continues until the process finishes execution. This movement between queues is what keeps the system efficient. Without these queues, processes would either block the CPU unnecessarily or interfere with each other. Let's take a real world scenario to tie everything together. Imagine you are watching a video, downloading a file, and typing a document at the same time. The video player process might frequently go to the device queue to fetch data from disk or network. The download process is also heavily dependent on I/O, so it keeps moving between the device queue and ready queue. Meanwhile, the text editor might mostly stay in the ready queue, waiting for CPU time whenever you type. The operating system constantly shifts these processes between queues, making sure the CPU is always busy and no resource is wasted. This is the core idea behind efficient CPU scheduling. One more subtle but important point is that these queues are not just conceptual. Internally, the OS maintains data structures for them, often using linked lists. Each process has a control block, which we discussed earlier, and these blocks are linked together to form queues. So when we say a process is in the ready queue, it literally means its process control block is part of that queue structure. In summary, these scheduling queues act like organized waiting areas. The job queue keeps track of all processes in the system. The ready queue holds processes that are prepared to run. And the device queue handles processes waiting for I/O operations. Together, they ensure smooth multitasking, efficient CPU utilization, and a responsive system. As we move forward into scheduling algorithms, you'll see how the OS decides which process to pick from the ready queue. But for now, understanding these queues gives you a clear picture of how processes flow inside the system without creating chaos. That is it for this video. See you in the next one.